At the highest level, our system, the fourth power thermal battery, makes the grid reliable. You can dispatch energy to the grid whenever people want it. Our battery can basically keep the grid going for weeks at a time. We are probably the only ones on Earth that actually know how to do it and do it right. I'm Dr. Asegun Henry. I am a professor in mechanical engineering at MIT. I'm the founder and chief technologist of Fourth Power. So the way the system works is we take in electricity. We, of course, want it to come from renewable energy. And we use that electricity to run effectively a giant light bulb, a joule heating element. So it's a large graphite element that heats up. It's like a resistor that has electricity flowing through it and it heats up to about half the temperature of the sun, about 2,500 degrees Celsius. That heating element is positioned next to some graphite plumbing that has liquid tin flowing into it. So the tin flows in at about 1,900 degrees Celsius. All the light being emitted by that heating element then heats the tin up to 2,400 degrees Celsius when it exits. The tin then flows over to the graphite storage blocks, which is where we're storing the energy, and they're made out of a lower grade of graphite that's very cheap. As the tin flows in the tubes past the graphite blocks, those tubes are radiating light, causing those blocks to heat up nominally from 1900 C all the way up to the peak temperature of 2400 C. And so when the blocks reach 2400 C, the entire system is considered fully charged. The entire system is encased in a very large layer of thermal insulation. So now the energy can sit there weeks and months. We lose about 1% of the energy we're storing over the course of an entire day. When you now want electricity back on the grid, you now use that big bank of graphite blocks like a heater. And what it does is it keeps the liquid metal hot, and we pump it through. The liquid metal comes out at 2400 C, and then it goes over to what we call our Thermophotovoltaic, or TPV, power block. The TPV power block essentially has a bunch of graphite tubes and panels that radiate light onto solar cells, which we call thermophotovoltaics. These TPV cells have a special design in the sense that they are attuned to the light that's coming out at now half the temperature of the sun. But instead of being 93 million miles away, instead our heat source is only a few inches away. And so that allows the light put onto the cells to be extremely intense. And in fact, that's the light that scales with temperature to the fourth power. With that extremely intense light, we now get a lot of power output from very little cells. And so that electricity coming out of those solar cells then goes back to the grid and keeps the grid going for as long as you need. Each of the individual TPV cells is about 1 square centimeter, has an output of about 2 volts and between 5 and 10 amps. On our module, there's 120 cells that are linked in series, and you get about 2 kilowatts coming out of that one little module. To put that in perspective, one of those modules is enough to power 1 or 2 houses. Each of those modules are then mounted onto the PowerStick. The PowerStick is a long aluminum extrusion that has about 100 modules on it. So you get between 100 and 200 kilowatts of power on each power stick. That power stick is then mounted onto an actuator, and that stick can now be actuated down into the light, or we can pull it back out of the light. And these light cavities, or think of it like a furnace, these furnaces are powered by the liquid metal flowing in the walls, keeps the furnace really hot, and we can control the output power of the battery by how far we dip the cells into the light or pull it back out. So that gives us one measure of control. The second measure of control we have is the liquid metal. If we actually flow the metal faster or slower, we can change the temperature profile in that furnace. The reason we can push the temperature up so high and others can't is because if you put TPV cells next to something above 2000 degrees centigrade, you're gonna see material that's being evaporated, or let's say sublimated, from the hot side, and it's gonna deposit on the TPV. And ultimately that coating of the material is going to prevent light from getting in, and you're not going to get any output. We have a solution to that problem. It's a patented solution, actually. We call it the sweeping noble gas curtain. The velocities at which matter diffuses through a gas is actually quite slow. And so if you just blow gas over the surface of the PV, you can overwhelm that speed and sweep away anything that was going to deposit before it has a chance to reach the cells. And so in this power stick, We also have the gas delivery integrated into the PowerStick. So there's gas flowing down the stick that's distributed along all the PV cells that's blowing across the cells, keeping them clean so that they can operate without having any obstructed material getting deposited on them. What's new in the way that we're doing it is that by pushing the temperature so high, it allows the threshold for where you get the electricity out, which frequencies of light actually give you electricity. We've been able to push that energy higher and higher and higher. And by pushing it higher, it actually moved the cell efficiency pretty far up. So for about 40 years, the efficiency of TPV was a little bit lower than 30%. When we were able to push the band gap of the cells higher, we actually demonstrated 40%. And we're actually integrating a new innovation from some colleagues of mine. So any of the light that's not converted gets reflected and goes back to our sun. But in our case, because our sun is trapped inside of a box, anything you don't use, we get to reuse later. So we're actually working with some collaborators to improve the reflectivity and the quality of our mirror so that we can preserve even more of that light, and that pushes the efficiency above 50%. The way we do our sealing is really our secret sauce. The seals ultimately are what keep the liquid metal contained in our system and don't have it leaking out every time we join two pipes. And I think we are probably the only ones on Earth that actually know how to do it and do it right. Cost is the key. The battery is 98% by mass made out of carbon, one element. That element is ubiquitously available all over the Earth, and it's very, very low cost. One of the things that was clear in my conversations with utilities, they wanted a technology that's not only low cost, but flexible. The ability to essentially perfect one basic box of technology that you can then replicate and rinse and repeat, and people can configure it in the way that they want. They can order however many boxes they need to meet their specific needs on a specific site. At the end of the day, utilities are charged with two basic tasks: to deliver energy at the lowest possible costs, and number two, to ensure that that energy is available reliably. Renewables solve one problem. They're now the cheapest source of putting energy onto the grid. And so now the challenge is really shifting to how do you deliver it reliably, and that is the problem that the Fourth Power thermal battery solves.